Hello, I'm Emily Fuhrman. I'm a freelance data visualization designer and developer, as well as a master's student in the Department of English and Comparative Literature here at Columbia. So the work I do focuses on building data-driven visual systems across a range of different contexts, both static and dynamic. And independently, I'm interested in experimental approaches to data visualization, dissecting perspectival constructs, and leveraging non-digital mediums to encode information. And I'm going to take a slightly different approach to my talk today, in that the data I'm talking about will be smaller and fuzzier, and I simultaneously want to examine visualization as a practice that produces a certain kind of artifact. So to start, I'll just clarify exactly what I'll be talking about in terms of uncertainty and ambiguity, because those are both by nature not clear things. So at least my focus and my subject matter are on the clear side. As a practice, data visualization rests on visual disambiguation. Given the tools that we have, that disambiguation tends to take the form of points, lines, and polygons, or other more inventive combinations of clearly delimited shapes and visual elements. And while formal approaches to representing the values of a given data set are integral to giving it a graphical configuration, what I want to address today is the importance of critically adopting a set of visual conventions that relies on demarcating any sort of boundary, but especially when focusing on visualizing qualitative relationships. And on a related note, the techniques and ideas I want to speak about, I think, gesture toward a broader need within the visualization community as a whole to more frequently visually acknowledge the ambiguity that inheres in the whole data wrangling process, from attribute operationalization to a final polished visualization. And I feel like those conversations tend to take place more often in geo-visualization than they do in non-geo-visualization. So I lumped qualitative relationships and uncertainty together because both are ambiguous. And with that in mind, I'm going to address three broad interconnected areas. First, I want to talk about the nature of the space that visualization as a practice constructs, which is associated with, but not limited to, conventions tied to web-based contexts. Second, I want to talk about some practical approaches to accommodating uncertainty when visualizing data, less as some sort of exhaustive summary of all of the things you can do, and more to point towards a couple of techniques that would prevent you from necessarily quashing out differences in a data set, even though, of course, as visualizers, that's what we're inclined to do. And finally, I want to share a project I worked on within the past year, for which accounting for ambiguity and representing qualitative relationships was integral to the final result. So I want to do a somewhat technical deep dive into that, just because I think the process behind deciding what the visual framework would be, as well as the technology to use, brought in a lot of these questions that I'll be addressing first. So in order to just define my terminology, when I use the term qualitative, I'm referring to data that's not gathered in a numerical form. It may be gathered using descriptive, open-ended, or unstructured techniques, and will typically have both comparative and superlative forms, as opposed to classification, which does not. And of course, quantitative data, by contrast, is gathered in a numerical form and can be measured in a standard set of units. And when I use the term uncertainty, I'm referring to the level of confidence explicitly associated with the values of an attribute. And uncertainty can come up differently when working with qualitative or quantitative data, or qualitative or quantitative variables. But in each context, it's worth noting that aggregation and categorization implicitly introduce variability into a data set that you're working with, irrespective of data quality. And I'm not acknowledging this type of uncertainty to say that somehow raw data in its messiest form should be visualized. Rather, I just want to foreground the fact that processing data necessitates imposing a semblance of order on what can seem like apparent chaos. And that's in order to enable an analyst or a researcher to discern visible patterns, or, as it were, make certain patterns visible. And I think that too often we allow data to have an implicit authority. When working with data that focuses on attributes that are more difficult to quantify, the nature of uncertainty becomes a messy process of trying to smooth over the variability associated with information that was difficult to measure from the outset. And explicitly speaking, uncertainty in its most observable form surfaces, as I mentioned before, in the confidence associated with the values of an attribute. Finally, when I use the term ambiguity, I'm referring to inexactness. Qualitative data is ambiguous in the sense that it captures information not defined by a standardized set of units. Uncertainty is ambiguous because it concerns the recorded value of a variable that is known to be an estimate, a buffered range, an abstraction, or a guess. Despite the fact that data seems explicitly ambiguous in fields such as the humanities, not to throw it under the bus, which tends to be steeped in mutability and nuance and interpretation, necessarily so, keeping in mind the type of space you build with a visualization is a valuable thing to consider in any context, no matter how clearly predefined. And it's important to consider because the space that we build constructs a perspective for the viewer. It determines the information that the viewer sees, the scope of what they see, and their distance from the data itself, which includes any intermediary calculations, transformations, or filtering that was deemed necessary on the back end. The space we build also demarcates the space within which we make an argument. And it's worth briefly touching on some of the reasons this is prevalent. Jacques Bertin's tome on information design, Semiology of Graphics, is an impressively exhaustive guide to the graphical methods one can use to represent differences within a data set. And Bertin is best known for introducing the 7 visual variables, which are location, size, value, texture, color, orientation, and shape, which can be used to encode corresponding values in a graphical context. Other visual variables have since been added to this list, but these are the original and I would say the handiest ones that I use most frequently. And despite my love for Bertin's methods and the frequency with which I use them in my own work, and despite the argumentative benefits of visual disambiguation that's proffered by these variables, graphical categorization rests on re-representing the categories that data processing implies to be distinct, whether drawing them further apart from one another or drawing them closer together as need be in order to convey something to the viewer. Basically, the visual elements you use to illustrate the elements of a data set paint the data set elements in relation to one another. And this isn't a giant surprise, and it's not necessarily bad or even avoidable because people write editorials. Like that's how things go. But there's, I believe, an air of this automated comprehensiveness that accompanies computationally generated graphics, which seems to superficially distance the graphics themselves from the intentions of the person who created them. And this consideration is not limited to the web. But it does seem that the prevalence of interactive visualization, web-based or not, inflects our relationship to data in a manner that paints data, no matter the context, as self-evident and somehow less prone to the fallibility that we would associate with the human who gathered it in the first place. Simply speaking, we're used to seeing stable spaces, which represent things to us clearly. And one thing I don't see as much, though, which, as I alluded to before, I do see more in the geovisualization community, and which we actually saw a little bit of yesterday during the keynote. What I don't see as much is the inclination to question their stability in a critical way. Visualizations tend to take the form of snackable content, to use a favorite and ridiculous agency buzzword, which basically means that they often are artifacts that we can revisit whenever we feel like grazing on information. We can put them down or pick them up at will without too much effort, and they're satisfying because they show us everything at once in all of its complex glory. Furthermore, interactive visualizations empower us to move things around and to even control, to an extent, what we see. They gratify our need to understand data as both a concept and as a material that has the power to reveal things without making evident their messier roots. As visualization practitioners, of course, we're inclined to choose clarity and simplicity because that's the whole point. Even if that entails downplaying like the one messy outlier that keeps trying to mess everything up, or the hoops we had to jump through in order to get a messy, incomplete data set to appear complete. Given the few visual variables we do have to play with, an element that differs from its peers will stand out among elements that share the same graphical plane, and that's just the nature of the spaces we build. The spaces that we work in have a way of calling attention to anomalies, for better or for worse. And normally, if we're creating a visualization for someone other than ourselves, we're creating it to support an argument we're making, however subtle, implicit, conventional, or overtly contrarian that happens to be. There is a fair amount of talk about scopic regimes and mapping, and work being done in the domain of critical and feminist GIS. And I don't plan to explicitly address considerations of power because there's a lot of good literature on that already. But I do want to encourage a less stable understanding of space, both in geographic and non-geographic contexts. And I think that one step forward in doing that is by accommodating some of the messiness we would normally try to subdue. So the question then becomes, how might we leverage Bertin's visual variables to less rigidly demarcate space? Alan McEachran has some thoughts on this, and if we focus solely on uncertainty for the moment, in McEachran's article that specifically addresses visualizing uncertainty, which is appropriately entitled Visualizing Uncertain Information, he states this, that of Bertin's original graphic variables, size and value are most appropriate for depicting uncertainty numerical information, while color, hue, shape, and perhaps orientation can be used for uncertainty in nominal information. And I think the distinctions here are interesting as a starting point. They don't comprise McEachran's entire perspective, but my first impression is that using size and value to encode something like an uncertainty score, if uncertainty is indeed recorded as a continuous variable, it makes sense, since one might normally employ these visual variables to represent other continuous variables, such as magnitude or population density. On the other hand, though, it doesn't seem to really offer something different that evokes a sense of less confidence when you look at this admittedly very small but still clear selection of shapes. I mean, in looking at a diagram like this, I don't really assume that either the top or the bottom circles have anything implicitly open to question about them. And I think that they leverage properties that might be too conventionally used for certain kinds of values to be effective. In addition, I like McEachran's suggestion for nominal information and think that there's certainly a place for representing uncertainty in this context as either an ordinal value, a binary value, or again, as a score. In particular, given the visual variables we might be leveraging to distinguish categories of elements, orientation or shape seem the most useful to employ alongside, for example, color, which we often use to distinguish overarching categories. But more than any other part of the article, the portion I found most interesting was McEachran's addition of focus as a variable to play with, which opens up what I think are more possibilities for directly evoking the uncertainty of a given value by fuzzing out some of the very clearly bound edges that, that normally you would use to draw shapes. And I think that while these are relatively often encountered in GIS-specific contexts, they're certainly applicable to non-geographic visualization as well. So, a few different approaches to altering the focus as a variable within a visualization. We, of course, have fill clarity here as one, in which the fill of a given element differs from its contour based on the uncertainty associated with its value. There's contour crispness, which varies the crispness or fuzziness of the outline of a shape. This is, I pulled McEachran's somewhat low-res representations here, but I think they do the job. And another one he mentions is fog, which I have mixed feelings about, but which I included for good measure nonetheless. In this case, we add a hazy layer between the viewer and the visualization itself. And while this technique does not directly alter elements on the page or the screen, as it were, it does add a foggy barrier between you and it, which suggests that there's something you cannot see as clearly as the rest. So these are a few different directions to take that I think are not commonplace, but often seen in mapping. But I don't come across these as much in non-geographic visualization. If we turn back to the data side, the biggest issue to deal with is how to quantify non-quantitative concepts you want to represent. And I mean that in a very utilitarian sense. If you're constructing a graphic that will represent elements with certain uncertain attributes, some measure needs to determine the level of fuzziness, for example, in the outline of an element, or the extents of the foggy region you plan to impose on your graphic. At some point, we need to reduce ambiguous values to numbers in order to work with them computationally. And to make a qualitative variable a quantitative one may simply entail converting it into a measurable value based on your knowledge of the subject. And this is an approach that I and the team I worked with took for the graphic I'm going to walk through in a minute. And in terms of uncertainty, my go-to approach, and I think many people's go-to approach, is to just make uncertainty itself into a variable, and which enables you to then visually encode that level of confidence associated with a value in some of the ways maybe that McEachran discussed. And then you can go from there. And finally, I just wanted to give a brief nod to interactivity, though I myself haven't experimented as much with ways to play with interaction or animation to to accommodate uncertainty or ambiguity. Interactivity does bring with it the potential for motion, as well as for interesting user feedback, which, again, we did leverage a tiny bit of that in the project I'm going to talk about, but a few potential routes to explore on the animation front might involve playing with speed or frequency or flicker or direction. I mean, there are a lot of possibilities, but it's a new dimension, a new malleable dimension that's interesting to explore. There's also a question which we touched upon yesterday regarding annotation and the type of legend that's appropriate to include in an interactive. And while I'm not by any means an authority on what should be presented to a user who first encounters an interactive graphic, or what a user might need to know upon immediately navigating to a visualization, I do believe that, of course, citing sources, as well as explicitly providing information regarding data processing, encourage a healthy skepticism within visual representation, though, of course, that tends to not be the number one priority of a visualization maker. But nonetheless, it's a good sentiment to put out there, I think. So I want to turn now to the project I mentioned, which will provide a better walkthrough on one way to deal with the question of qualitative relationships. So towards the end of last summer, I worked with Quanta Magazine, which is an editorially independent publication of the Simons Foundation, to create a representation of the theories of everything, which was essentially all of the major topics in physics and the theories associated with each topic, as well as the relationships and overlaps between the topics themselves and the interconnectivity between theories. And the broader aim of the project was to create a graphic that could both tie together the content of the website, as in include links to articles that were published over the lifespan of the publication, but which might address related things despite how far apart they were in time, and serve as a fun educational reference for readers, which would grow in complexity as the site added additional content. And one less than great aspect of this that I should just note is that technical constraints prevented us from making this iframed graphic a sort of automated aggregator of information on the site, which I think would have leveled it up. Everything did have to be hard-coded, but that turned out to not be a huge issue because the major topics in physics have been pretty persistent and will likely continue to be, and then the way the theories were built into the interactive would enable the updating of the data set down the road if need be. So really the most difficult aspect of the project was in representing topics that had no distinct size or standardized measure of significance. These numbers don't seem very big, but if you have, I'll show the data in its original form in a second, but if you have a list of topics and the knowledge that some are more talked about or focused on than others, and you vaguely see them as umbrellas over different types of theories, it can be a really difficult set of conceptual challenges to grapple with, especially when you're trying to make something so vague in a data sense, very concrete and explorable. Each of these topics had any number of theories associated with it, and there was a hierarchy between them in that topics contained theories. And the interrelationships between theories and topics needed separate methods of representation, because this is going to get very excessively specific, but it's maybe will be clearer looking at the graphic itself. Topic relationships did not always have a real bearing on theory relationships, the theories that were contained within them. Two theories within a topic might be related to theories within other topics, but not to each other, for instance, because that theory and other theories had their roots in a single other theory. So, it wasn't the kind of thing where the topic a theory was associated with would determine its relationship to other theories. And you couldn't assume that there were direct linkages between theories contained in broader topics. So here's what the original data looked like, which was a fun collection of descriptive paragraphs in a Word document, actually like a completely nightmarish representation of topics. And basically the furthest left indented blocks of gray text are topics, and then the nested blocks of gray text are the theories associated with that topic. There were a couple cases in which there were duplicates, where different versions of the same theory, for example, might show up under two different topics. And if you're working with theory IDs, for example, that necessitated adding an extra layer of intelligence to the interactive itself. But basically, this was all the content that needed to make it into this final interactive, text included, because we not only wanted to provide a picture of what physics as a field looked like, we wanted to be able to engage readers by explaining in some depth what each one was, with thankfully word count limitations, but still it was quite a bit, and it took a while to come up with a good way to fold all of this away in a meaningful, elegant way. So I'd mentioned the problem of topic size before. If you recall the 12 topics in that sparse slide, I showed a few slides earlier. Topic size we ended up dealing with by making topic significance into a variable, as well as this secondary, both technical and conceptual problem of overlap between topics. We created two different data sets, one in which topics were just listed out with a value for significance, and then another in which any topics that were related in a certain way would be linked together and given a score of degree of overlap. So that was an iterative process that involved talking to a lot of scientists and researchers and just coming up with the semblance of a list that everyone could agree on. But since each of those variables were essentially qualitative, in order for me to take them and feed them into some sort of web-based graphic, they had to have values for me to read. And just as a diversion for anyone interested, I built all of this in D3. So D3 was my go-to from the beginning. And while it wasn't clear at the outset whether or not we would be able to use an out-of-the-box graphic, I was gravitating towards the force-directed graph, if anyone's used it before, and the final product ended up being a very hacked version of a few of those. So that's just some background. The graphic itself was not claiming in any way to be the be-all, end-all of the field, or to represent the entirety of the physics world in a way that was impervious to dispute. But it did seek to be as comprehensive and as accurate as possible, and we tried to make that clear in the accompanying article, accompanying the interactive. So rather than annotate all of that within the interactive itself, we relied on the text of the article to make that clear. So I'm going to show my very, very, very first pass at this, which is hideous, but there you go. I used okay, so this is, at this point, we'd scored every topic in physics on a scale, I think, of 1 to 20, say. So every topic here was, I guess, quantum gravity probably had a score of 18 or something. The size of each circle just pulled directly from whatever that value was. And I think I used some vaguely D3-based Venn diagram generator for this, kind of just to see what it would do with the overlaps I defined. And I guess somewhere in there, it was clearly reading what the relationships between these topics were, but I mean, the strong CP bubble down there, it appears nested within these bigger circles, and it's just, I mean, it's an unreadable mess, basically. And I think that was largely in part due to the circle as a shape, which isn't so flexible in terms of being able to overlap other surrounding shapes. This made it clear that we really needed something more malleable, but working within SVG as we were, and as D3 is very conducive to, makes malleability difficult to code. A second reflex was to resort to a node link diagram here, because if you think about it, it makes sense. You have a series of nodes of varying degrees of significance, and you have relationships between them that you'd like to account for. And taking a network approach would both give you the terrain and account for links between different topics. You could also size by radius, as it were. And there were a couple of issues with this that I wasn't super comfortable with right off the bat. And the main one was, aside from its oversimplification, I didn't like the fact that the relationship between these two topics was represented as its own discrete shape. We really wanted to evoke a sense of overlapping topics, even in a very literal way. And this seemed detached and didn't really enable us to encode strength or closeness. Yes, we could have varied the line width, for example, to maybe make some relationships heavier than others, but it was a limited approach. But I tried it anyway, just as a starting point, and this was a first attempt to represent all of these topics and their relationships using the D3 force-directed graph. And it's fine in that, I mean, this was especially useful because it generated a smart layout that spaced things out in a way that would have taken me forever to do manually. Without breaking my display, I want to just quickly pull up the force-directed graph in D3 for those who haven't seen it before. It's like this. It's got some nice built-in physics, and you can vary the amount of repulsion between nodes so that you can have this help you generate a nicely spaced out network. That would be a pain to do if you were doing it manually. So this was the initial lay of the land, and it wasn't suitable for our purposes. But around this time, the problem of overlaps started to become really started to worry me, because drawing a path dynamically like this, I don't know. I went through a number of different approaches, including, extrapolating neighbor nodes from some Delano triangulation setup, and some of the models I came up with before deciding on this final method would generate properly in the browser maybe 95% of the time, but that extra 5%, a topic would not overlap a topic it was supposed to, or a theory would fall outside of the graphic itself, and none of the methods that I tried out in this somewhat limited, bounded SVG world were really sustainable or gave me confidence, I guess. But finally, given the overlap metric as well as the significance one, I came up with this sort of deal where I would use the D3 generated link between nodes as a sort of measuring stick from which to draw, as you would a compass, from which to determine the vertex of a line I would draw around each node. So that way I could both control how big a node appeared in this vague shape I was drawing around it, and I could, to a certain extent, control the degree of overlap between nodes. So I don't know if that's clear or not, but for quantum gravity, for example, assuming it was supposed to look big in this map, I could take its significance score, and then, knowing that this link was between it and the hierarchy problem, I could take the overlap score between those and kind of work it into the calculation and decide that that point on the line was the best place to put a vertex for the hull surrounding that node. Conversely, I could do that for the hierarchy problem as well, and this was a neat solution because with the network as a skeleton, I had all of these like pre-spaced lines accounting for every relationship, and I guess we were lucky in the sense that there were no really, really bizarre overlaps, and that I didn't have to worry about drawing a shape that would be like, you know, ridiculous like around the whole thing. We were lucky in that it could be pretty self-contained, and that this method would give us what we needed, while still leveraging the built-in functionality of the force-directed graph. So here's the initial stages of that. You obviously can still see the network diagram underneath here. But also, I mean, yeah, you can sort of see how I was using the links emanating from a given node to draw these blobbier shapes around the perfect circles. And it took some trial and error in terms of over-representing or under-representing certain things, but it turned out to be a good solution. This is another snapshot of a pretty ugly pass at an interface. As you remember from the Word doc, there was lots of text to deal with here, and just to have it on there as visual feedback for me to make sure that everything was linking up correctly, it sort of aligned it around the budding visualization like this, but it was way too busy for the final product. You can also see here this internal network that I ended up using to represent theories within topics. This is yet another D3 force-directed graph overlaid on top of the original one which had the lines drawn around it. In this case, I was able to use the X and Y coordinates of those topic nodes and set them as little like gravitational focus points for the overlaying force-directed graph. So I could use the positions of the topic underneath to get theories, the little nodes, to hover around the topic they were associated with. And that wasn't perfect because occasionally it gave rise to this like eggs in a basket kind of view, which nobody liked that much. But at the end of the day, this image shows that more clearly. It turned out to be a necessary, a pretty necessary compromise in the long run. You'll also see how on edge cases, like topics that edge cases like this, topics along the edge that didn't have any relationships going like this way that would help draw the shape out, I had to put in some like dummy buffer nodes there to get the shape to draw properly, but that's getting excessively detailed. So the final version looks like this, and I'll pull it up live now so you can get the full experience. This was art directed by Elena Shmahalo, who is a Quanta employee, and the gradient in the background was simply to create a space, so it's not symbolic of anything. So, my local version. And adding to this, adding this kind of fisheye effect to it, you could zoom in to a given topic. The sub-theory nodes will kind of rearrange themselves in a browsable list, and you could click on those in addition to get a description on the right. And as far as just programmatically handling the kind of data we were working with, this, I was happy with this setup despite occasional busyness or overlapping of nodes. When you're working with something with an unpredictable physics simulation, some weirdness will come to the fore, and it does a little bit here. But all in all, it's a pretty nice way, I think, to browse what started off as a really difficult quantity of information to delve into. And finally, there are certainly weaknesses with this visualization. You'll notice that in some previous versions, I did retain the dotted line outline for topics, which would seem right since they're not clearly defined by standardized units. Ultimately, this was just a design decision to make them solid. But we hoped the mutability and the blobbiness of the visualization as a whole would sort of enforce that these shapes were not fixed. So, for better or for worse, that's what that is. And I mean, SVG as a whole is not especially conducive to building vague things because it's based in ratios and whatnot. One little piece of the interface here that I might as well just address. This isn't true in my local copy, but we did end up adding in upvoting, which was a weird, I don't know. I thought it was a weird thing to add to a graphic like this, and a strange way to empower any users who might be browsing it. But ultimately, the idea was to allow readers to vote on their favorite theories and perhaps construct a leaderboard of some sort. So within the topics, the little theories down here will order based on the number of votes they have, but that's a little subtle thing I built in, so. But now you know, now it's there. Any of the links on the sides lead to articles where you can read more about a given theory or topic. And yeah, I think that's pretty much covers it. Yeah, I can use the rest of my time to take any questions anyone has.
Got a question. So you're trying to, if I understand, produce a network of kind of relatedness between these different physics theories. And of course, like in evolutionary biology, like it's all about building relationships between things. So I wondered if you could kind of, like the standard way of depicting that is a bifurcating tree. You know, both species and languages have histories, and depending on how recently they diverge from each other, produce nested system relationship. But then there are things like hybridization and horizontal gene transfer that cause it to become a network.
Yeah.
So there's this kind of there's a kind of attempts to develop network approaches to depict the evolution of relationships in the biological context. I was just wondering if the kinds of things you're doing could be kind of applied to that, and also whether or not you could take a sort of simplistic bifurcating tree-based approach based on the similarity of those theories that you had. Was it 21? I don't remember how many.
41, I think.
41. And like split them up and turn them into binary characters and
Yeah.
build a kind of most parsimonious tree that shows kind of potentially the evolutionary history and relatedness of those theories. That would be one way of doing it.
Yeah, no, I mean, that would definitely add a level of granularity to this graphic that we hadn't anticipated building in. And I wonder too, given the admittedly simple hierarchies it does represent, that sounds like a different visualization. Like, that sounds like something I wouldn't necessarily want to put in here because it would be imposing a different temporality on something that didn't really have one before then. But depending on the context, that would
You don't want to like emphasize the time and historical development as the kind of unifying discipline.
I think that would be a great perspective to take. I feel like it would not look like this though, if that were the goal. It would be completely different. It would be more directional. This is just kind of floating here as though it's like the static state of things. If I were going to emphasize progression or temporality more, I would certainly have this appear to be more of a progression for time. But yeah.